Hello, welcome to our brand new episode of Corecast. I'm your host, Tim.
And I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And also, if you're on YouTube watching this, do ask us questions during the episode so we can get to them. Also, just to let you know, if you're watching this offline, or rather not in the moment right now, we do this live every Tuesday at 5 p.m. or 8 p.m. Eastern. So do join us if you can. So without further ado, let's get to it. So I guess Mikey, I'm just gonna pick on you. I was reading several books about space-time being doomed, and that sounded very bizarre to me, like that space-time doesn't really exist. But I clearly see it. I exist in it. I can move my arm in 3D. I perceive time. Like, what gives?
You read books on that? I'd be surprised it doesn't. It's something that's not well known. The fact that space-time is doomed. Most
There is a
people have
book.
no idea. Yeah. But I think maybe the best way would be to just kind of unpack what you just said about what our presumptions about space-time are, right? Like it's one of the oldest. Like even when you're born, probably we're like ingrained with this idea that like there's some environment around us, right? And we can move from one location to another, and location is a thing. I don't know. You could think about it like a fish swimming in water, right? The water is like their medium of existence, and we don't exist in water, but in a similar way, we can kind of imagine that we're like um, moving around in this canvas, right? And I can go from one location of this canvas to another location of this canvas, and I can be closer to you or I can get further apart from you. But the idea is that you have a location and I have a location, and that determines some notion of distance in space between us. Um, and the typical story says that this is a smooth canvas. I can be far from you, and I can get closer to you and closer to you and closer to you as I move, and that's a real thing. Um, and this was, I guess, first formalized by Newton, who was the first person who drew that Cartesian grid and actually defined distances as being this continuous thing. Like I can be 10 meters from you, and then I move closer, I'm 9 meters to you, move closer, and I'm 8 meters to you. Um, this whole idea of a smooth kind of background where actions take place has been kind of like a pedestal of just, not just physics, but also philosophy and also just, human intuition for a long time. Um, but it seems like this picture breaks down at a certain point. There's no way that this idea of a smooth space, this description of space as us moving through it in a continuous way, there's no way that that holds down if you zoom in far enough, like to microscopic distances.
Yeah, yeah. Actually, I want to challenge that a little bit though. Even quantum mechanics, which is at super small scales, like deals with space and time itself.
It
So,
does, yeah.
like, you're telling me there's no space and time, or like that
Yeah,
doesn't
so
make sense. What gives?
right, so quantum mechanics does deal with space and time, um, and that's true.
I
How does quantum mechanics deal with space and time?
yeah,
Can you want
I
to jump in, or?
I think you're not going far enough. Like the basic quantum physics, the one of the assumption is that there exist objects on space-time, right? Like already the fact that space-time exists is a given, right? So to some extent, to see this paradox, we kind of have to break quantum physics a little bit. We kind of even have to break down the at least the most basic form of quantum physics. And it turns out that when you do that, space-time is kind of broken.
What?
Yeah, Tim's right. Like, so space-time is kind of like an assumption for quantum mechanics, but then if you take quantum mechanics to its logical extreme, it literally destroys the space-time itself. So the theory literally kind of breaks itself.
Yep.
So can you guys walk me through like how do you know that? Like that sounds a little hooey to me. Like what's going on with that? Like how do you know that space itself doesn't really exist? Walk me through a thought experiment.
So this rests on the uncertainty principle, right? So I
Mhm.
think maybe a thorough discussion of the uncertainty principle. Like this is something that we learn in high school, right? And it's taught in many different ways. Um, But fundamentally, what it means is that um, if you try to determine the precise location uh, of a particle, the more precise you try to localize it, um, the more uncertainty you're going to see in that measurement.
Yeah,
Well,
let me just add that. I think one of the point that's missing is, in order for you to see something that's progressively smaller, that object itself has to be kind of be smaller than the resolution itself, right? Like you can't use a baseball to try to see like where the ping pong is, basically. Like you're gonna just if you throw a baseball, sorry, like a basketball. Let's make it bigger. If you throw a basketball at a ping pong ball, the ping pong ball is just gonna bounce right off. You're not gonna find out where the ping pong ball is, right? And the thing is, and the thing is, in quantum physics, one thing we have to accept is that the smaller the object is, the more unruly that object becomes, the more energy it contains. It's almost like if you pocket all that quantum goodness in a smaller size, it just couldn't help but it just cannot contain itself, right? And so kind of and that tells you there's sort of this limit. If you go to the extremely small, you have to pack all this stuff in a smaller and smaller distance, and the energy becomes so large, and then at some point it's gonna break, basically.
Yeah, we can unpack that a little bit too, right? I think I like that train of thought. So imagine you're trying to measure the size of something that's really small, right? As Tim mentioned, if you're trying to measure the size of um, I don't know, something small like a small marble, right? You can't throw a baseball at it, right? If you want to measure something that's very small, you have to use a very small instrument to measure it. So if you wanted to probe very small distances, a baseball would be good, but what will be better? A ping pong ball. What will be better? A tiny rock. That'll give you like more precision. But what's an even smaller object? So when we get to we can actually use particles, individual particles, which are pretty small, right? To try to get a sense for the precision and the distance between two objects. But what's smaller than an electron? A particle of light. That can be smaller than an electron. What's smaller than a particle of light? A more energetic particle of light. And what's smaller than that? A more energetic part. So there's this inverse relationship between energy and size that's basically a result of the fact that in quantum mechanics, things are represented by waves. So the smaller the wavelength, the higher the energy. And so in order to probe smaller distances, this necessarily requires you to deal with higher and higher energy objects.
And that's because energy and wavelength are inversely related to each other. So the shorter the wavelength, meaning the shorter the peaks and troughs are together, the shorter the wavelength, the higher the energy is. Is that correct?
Like literally, yes. So we know that if you remember from electromagnetism, blue light has a much smaller wavelength than red light. So if you wanted to see something in space using light, you could get a much better resolution using blue light rather than red light. The downside is that blue light is more energetic, so you're more likely to destroy the thing that you're looking at by shining blue light on it. So there's quantum mechanics predicts that there's this invariant trade-off between the precision with which you measure something and the violence with which you measure that thing.
Yeah, that sounds about right. Reminds me of a thing called femtophotography, where you send these like really bursts, these like short light pulses, and it destroys the sample that you're trying to observe. But anyway, that's a story for another day.
You get a measurement of it though, right?
Yeah, whatever state it is. But yeah, anyway, that's a slight digression. So I guess okay, so if you want to probe smaller scales, you have to probe it with something that like basically pack a large enough energy in a small enough space. Is that correct?
Yes. Yeah.
Okay. And what is like the extreme? Like, let's suppose I keep doing that. Like, what's gonna happen? What's the worst that can happen?
Right. So I think I should to try to measure something smaller and smaller and smaller, we have to use something more and more energetic, something more and more violent. And it turns out that there's a very special distance scale where if you try to probe that distance scale, that would require so much energy in such a small region that the region would just collapse into a black hole. For those that don't know about black holes, remember, anytime you get a sufficient amount of energy within a small enough space, it's going to make a black hole. There's just no way you can get around that. It's Einstein's equations determine that there's just this limit. Like there's like each region of space has like a maximum capacity for energy before it turns into a black hole. So it turns out that this exercise of just trying to look at space on a small distance below a certain point just gives you black holes everywhere.
So I actually want to challenge that slightly. So whenever I hear about black holes, yes, like I agree in principle. If you shove a small enough energy in a large enough energy in a small enough space, it in theory would form a black hole. But all the black holes we see are large. So like, how would you know that you would form a black hole? Like this seems all theoretical to me.
Yeah, so I think does require a little bit of a leap of faith. Like if you believe Einstein's equation to be correct, there's no reason why the equations of black holes wouldn't apply if you have a smaller region. So it does require a little bit of leap of faith. It would be really strange if Einstein's equation only applies to black holes of a particular size. And also we have a good reason, right? Like the reason we see the black holes the size that we see them is because typical black holes are caused by stars collapsing, and stars just cannot get that small. Right? So in this thought experiment, we're talking about microscopic black holes. These are quantum mechanical microscopic black holes. And if we have a super duper massive accelerator, maybe we can try that. But we don't have that budget or energy or technology right now. So these are not the same black holes.
I see. And I just want to ask for completeness. Let's say like you reach that minimum energy to form a black hole. What would happen if you throw in more energy? You're like, I'm just gonna destroy the black hole. Like, screw it.
You can
like,
make a bigger black hole.
Yep. You can't destroy black holes. That's like, it's almost like nature is playing a trick on you, right? Like if you accept quantum physics and you start with space-time, and literally you try to perform an experiment, because physics ultimately is experimental, right? You try to perform an experiment to measure this very thing that you postulate to exist. Like it literally breaks apart. Like when you make a black hole, space-time is so warped that it's literally like broken apart in some ways, right? Like there's a hole in the space-time, and it is broken. So it's like you think it's there, but you do an experiment, it's not quite there.
Well, you do an experiment and you see that the space eats itself, and then if you look at the theory, you see that this was inevitable, right? There's no way, even in principle, to probe a small space without getting a black hole. And so that tells you one of two things. Either that's just how space-time is, it's just microscopic black holes everywhere, or there's something we don't understand, that this description of space-time is not adequate any longer to describe what you're trying to do.
Yeah, so basically the theory is self-contradictory in some ways. That means it's
That's
missing.
Self-contradictory though. That's too strong, right?
Incomplete.
It's self-devouring.
Yeah, it's incomplete in some ways, right? Like something it thought to exist actually turns out to not exist. So you kind of have to rethink what was the thing that you thought existed, and that's space-time. Like you thought space-time is just a place for things to exist on, but then this can't be true anymore.
Yeah. So I guess like I want to kind of take a step back to like human experience and try to like relate it back. So I buy that like on a small scale, like you'll get a black hole if you measure. But if space really doesn't exist, I see my computer in front of me. It's like localized in a particular area. It's not here, and it's not like in Alpha Centauri, but it's like in front of me right now. How does this happen? Like why do I see things as if space exists? Like what gives?
Something approximately looking like space appears to emerge as you zoom out, built on something more fundamental that doesn't appear to resemble what we know to be continuous smooth space.
Yeah, I would say this is indeed a bit strange if you really think about it. If you actually look at some of the more fundamental laws, we see that in quantum physics, like there's a lot of randomness fluctuating, right? And if this sort of randomness reigns supreme in our world, then we're gonna see things popping in and out so random. Like Sahil might be on my left in one instance, and then all of a sudden on my other side in a different instance. If quantum mechanical effects dominate, this would be the case, right? But it turns out that for reasons that are actually not so clear, it's because we have lots and lots of particles. And when all these particles kind of come together in a quantum mechanical environment, something interesting happens. Something macroscopic happens. It's as if all these quantum mechanical systems come to some sort of consensus, right? And this and this process where the system comes to consensus kind of is able to localize these objects, right? Like imagine I have like 20,000 million, way more than that, particles in my hand, right? And each particle is kind of like a system, and it, in some sense, interacts with, let's say Sahil, if we were to meet up, right? Each of these particles has a sense on where Sahil is, right? And as long as these particles have a consensus that Sahil is like in a certain location, then we're gonna feel that Sahil is in that location, right? So to some extent, this notion of where things exist depends on this fact, depends on this macroscopic agreement of different particles, kind of, that and that such a location exists. But it's by no means fundamental.
It's almost like a majority vote, right?
Kind of, yes.
You need a majority vote to determine a location in space, and because we're made of, astronomically large numbers of particles, everything we deal with is kind of filtered through this lens of the vote, and that's why we think that locations exist. But it's true, even if you ignore this whole like space-time is doomed argument, the idea of location becomes fuzzy once you start looking in the microscopic level. But this is just like the ultimate extreme of that.
I see. So I guess like so far we've been talking about this in terms of space, where like this location is emergent. But what about time? Like, I clearly am seeing the screen. I'm seeing your mouth move from one instant to the next. And so like, why is there this notion of like time? And so far with the black hole, it seems like if you throw enough energy in a small enough space, black hole forms. But what does that have to do with time?
Yeah, I think so. Einstein's theory relates space and time, and by that logic, if space is broken when we create black holes, the same concept will apply to time. And for the audience who have seen maybe Interstellar, we know that when objects get too close to a black hole, their concept of time becomes very different from someone who's really far away from the black hole. So imagine you have an object that you want to see, whether it exists or not at a certain time, and in order for you to measure this time at a very precise time window, you kind of have to scramble really quickly and shoot some laser or whatever at that object, right? And when you do that, the same logic applies. In a very short amount of time, in order to scramble that quickly, you have to pack a lot of energy in. And when that happens, you create a black hole. And when that black hole is created, all the time just get messed up for that particle. So you can't really say like, at what time did the particle exist, or did the particle exist or not, right? So in that same way, you kind of mess up time as well. Space-time altogether, it's kind of broken when you make a black hole.
I see. So basically summarizing your 2 points that you made, one is locality, or like things existing in a particular location, has to do with us being macroscopic creatures, where a ginormous number of particles all agree on where everything is, and that's sort of coherent, at least from our perspective. And then what you're mentioning is that even in the case of time, if you want to measure it more and more finely, you have to throw larger and larger energy at it, at whatever the particle you're measuring, and at a certain point you throw enough energy, it becomes a black hole, and then you don't know what time is for that particle anymore.
Yep.
Yeah, in general, how can you? I mean, the way we usually determine time is by looking at some object that we know is, has some regular motion across space and measuring the amount of time it takes for that object to move across that space, right? Like a ticking clock, for example.
Mhm.
Yeah, it's just every single 60 seconds, the second hand is gonna go around once.
Yeah.
Um, it's not exactly clear how to measure the passage of time if we can reference space. I think this is kind of alluding to the connection that Einstein found, that these two things are basically the same thing.
Huh. Yeah, no, I agree with that. I guess like I also want to, sorry, I'm kind of jumping a little bit all over the place, but another point I wanted to understand is the concept of locality itself. Like where, what does it mean for macros, for all these particles to agree that something is here? It's not like they are conscious agents and they're like, hey, particle over here, let's both agree that this is here. Like everybody in my body, let's agree. Like there's there's no consciousness. So like, what gives?
Yeah, and I think it's just that if we look at the way physics works, physics interactions happens at least locally at a location and at a time. And this is also probably approximate in some ways, but at least that's what we
Yeah, that's
observe.
by design, though, right?
Yeah, that's sort of by design, and also what we observe, right? So so when the interactions themselves are so localized, e- so imagine a scenario. Imagine you kind of have like a bucket of water, right? And let's say there's a particle, and in quantum physics, this particle is probabilistic. It can be anywhere in this type of water, right? But the key point is it has to make a choice, right? Maybe it's on one end of the water bath. Maybe it's on the other end of the water bath. So so even though there's a probability for it to exist everywhere, in order for things to happen, for interaction to proceed, it has to choose a location, right? And once, let's say it's in location 1, 2, 3, right? Then if 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 we were to come to, let's say, a different agreement that let's say now the location is 2, 3, 4, this change has to incur some cost, some kind of energy cost or interactions, right? So even and so this consensus is kind of like a requirement in order for anything to happen. It the things that happen has to have a location, and when these interactions happen, the location becomes pinned down. If that makes sense, right? It's almost like, let's give an analogy. It's like playing a magic trick, right? Like magic is happening. Like let's say a magician give you a deck of cards, right? And if you don't choose a deck of cards, the magic will never happen, right? Like the magician tells you, hey, pick a card, so that we can do the magic trick. This is like the world. If the particle does not pick up a location, there will be no interaction. The world, nothing will be happening in the world, right? So it's kind of like, do you want to see the trick or do you not want to see the trick? It turns out that we do want to see the trick.
Fair, fair. We actually have an audience question. So, why do you think it is that the double slit experiment? Why do you think it is in the double slit experiment when we observe light that it changes its reaction? And do you think it's possible? Do you think it's possible radio waves bend around stars?
Well, let me just say that the double slit experiment exactly works in this scenario, right? Like if you're not looking at the particles, then the particles doesn't have to choose a location yet, right? There doesn't need to be a majority vote. So to some extent, anything can happen. And the moment you see a particle going through one slit as opposed to the other, kind of there has to be a majority vote going on. And this is the process of decoherence. And that's why you see, not to get into technical details, that's why you see certain patterns emerges and whatnot. And as opposed to radio waves, this is part of the standard Einstein's theory. Light can bend around massive objects just like particles. Light and particles are actually not very different from each other. It's just that light is a lot lighter, but they can bend around objects. They can change directions and so on and so forth. So
Gotcha.
Yeah. I would agree. Radio waves can definitely bend around stars. But I mean, going back to like Tim's water analogy, right? Like, if you're trying to pinpoint the location of a particle that's in a bath of water, right? Um, let's think about what happens if we reduce the density of that water to the point where there's just like one water molecule per square meter, right? We call that a gas, but we can still call that water if we want. But then it's going to be harder to pinpoint that location, right? Like, if the one water molecule bounces against the marble that you're trying to localize here, it's here. Next, you might find it here, here, here. That's kind of like what the uncertainty principle is telling us. But if you increase the density of the water, now you have thousands of water molecules hitting this marble every single second, or millions every second.
Yeah.
And that's where the majority vote comes from. They all kind of agree, and now you can start to pinpoint the location and say that this is here. But if you reduce the density, then its location becomes this kind of random thing, right?
Yeah, and I want to add that this is observed in the laboratory. If you have fewer particles, the spread of the location of a quantum mechanical object, it becomes more and more quantum mechanical, basically, right? So it tells you that the reason we see location as such a sharp construct is purely because we have a lot of particles, right, to have this majority vote. So
that makes sense.
We're a walking army.
Yep.
that makes a lot of sense. So I guess like now that you guys have shown that space and time is both kind of approximate and not truly fundamental, what does it get replaced with, or what are candidates to replace it with? Like what's beyond it?
Oh, that's a fun question.
That is a fun question. I'm gonna give you my favorite alternative, right? Like if you want to follow this trend to see what replaces space-time, you have to look at what happens when you break it, right? When you break the space apart, what's left, right? So then you have to look at black holes. What happens in black hole is that when you create black holes, the notion of location kind of get messed up, right? But you know that in black hole, there's this thing called quantum information that is preserved, right? And if you look at our other episode, like when you throw a particle in the black hole, the content of that particle is never gone, right? And in fact, because of Hawking radiation and so forth, this information can be stuck on the surface of the black hole. It can be extracted by Hawking radiation, and it can move around, right? So in a very real sense, it's almost like, the space-time got broken apart, and it can kind of move around in the universe, right? And one proposal is that this quantum information is actually linked by microscopic wormholes, right? So literally, space-time is sort of like a web of wormholes, and maybe that's a potential replacement, but we don't have detailed theories yet, but that's a really intriguing possibility. That would be my favorite replacement.
Yeah, it's a theory for which we don't have a lot of like strong evidence for, but it elegantly circumvents all of the issues related to this.
Wait, how does it circumvent the black hole issue, like throwing enough energy in a small enough space? You have these like web of wormholes.
Yeah. Well, in this case, it just tells you that space-time does not exist, right? Because space-time itself, when you zoom out, maybe it could be localized. But when you zoom in, space-time is something else. It could be extended objects stretched out. Like maybe wormholes are more fundamental in some sense. These extended objects that most of the time they're not extended, but they could be extended, right?
So actually, one thing that I just thought of in terms of this explanation of black holes forming is like when you actually perturb I don't know, whatever we're in at a small enough scale, but like if you just leave it alone, you really can't like see below. So is this like how would you be able to know like that this is there? Because you can't really, you have to like you don't have the option of probing it, otherwise a black hole will form.
How do we know what's there?
Like, so what I mean is like the whole argument about space-time not existing, at least from what you mentioned, is like if we throw like enough light or like enough energy of light or throw some type of energy in a small enough space, we'll create a black hole. So that's why space-time doesn't exist. but that's like you're interacting and like just bothering it. Like you're just mucking up nature. Like what if
Uh,
you just don't do anything?
if we didn't do anything, then we wouldn't know that this problem existed. I would say.
Yeah.
Yeah. It's by doing this mental thought experiment that kind of reveals the weakness of the description.
I mean, that's the funny thing, right? Like in physics, you have to do something to do a measurement. Like there's no free lunch. You can't just sit around.
If it free falls and no one hears it, does it exist?
Yeah, in physics, you have to make an observation. So like the molecules have to jiggle to see that sound wave. So something's got to give. If nothing interacts, then not an interesting universe. So it is what it is. If you want to observe something, you can shoot a massive beam of particles at it, create a black hole. The black hole will decay. You gather all the Hawking radiation, and you recompute and see what was there. You can try to do that, but not very precisely though.
Yeah, I think the way to say it is that like in the typical interpretation we just described, where you just take quantum mechanics and general relativity and try to put them together, you find that below a certain distance, you just can't say anything because of these, as Nima says, these damn black holes just keep basically blocking your ability to make any statements about anything. The wormhole description that Tim described is kind of a theory that's consistent with what we know, but also gives kind of an answer to this, saying that the space itself is not the fundamental entity, but the movement of information is what you should be paying attention to. So if you don't pay attention to the movement of information, you're just going to see black holes. But if you pay attention to the movement of information, then you're going to see what's actually going on.
Oh, very clever. Very clever.
Follow the information. This is the currency of physics. It's like follow the money.
We're basically we're basically looking at the wrong thing. If we just try to measure distances, then it's just gonna. If we just ask questions based on distance, then the theory is going to give you nonsense. But if we ask the right questions based on information, then it's going to give you something sensible.
I see. And so, okay, so to kind of wrap this all up, I want to kind of ask a more like human-centric type of question. So all the things that we're doing are based on like our sort of conscious experience and us creating models of this. So like how much of this is like basically constrained by the language of like our conscious brain versus like what's outside? Like this is totally a very philosophical type question, but I'm just curious to gauge your guys' thought. Why do you go? You never brought on your face.
Yeah, like I mean, I don't know. To me, it seems reminiscent of like the simulation hypothesis, right? Like the fact that a smooth space exists is very fortunate for us as macroscopic beings because it allows us to move around and do interesting things. And we know that at a certain point, this description stops making sense. There's a limit to this description, and so short of saying that we live in a simulation, it's just a very convenient fact that something like smooth space does emerge. We don't know why it emerges exactly right now, but we know that it's not. We know that there's something deeper than that. That's all.
Tim, you were going to say something.
Yeah, I would say. I mean, I would say usually physicists will give you a lot of like what's the word like. Maybe hate is a strong word, but like when these questions arise, usually physicists will be like, this has got nothing to do with psychology. We're doing physics here, okay, folks. We're doing physics, no psychology. But from that lens, I would just say that look, the brain from a physicist's perspective is nothing more than just some collection of particles. Like we are as intelligent as like a bunch of gas to some sense, maybe slightly more organized. Let's put it that way, right? From that lens, our observation of the world is simply based on this, classical world where when a lot of particles interacting together, they see a macroscopic world emerges, right? And I would say, at least personally, this kind of humbles you a little bit, right? Like you see that even even the quantum mechanical reality, they don't even care about humans, whether humans want a smooth world to exist or not. I mean, the world happens to be like this, right? But fundamental physics doesn't care. Like for all physics does, it could have been a really rough ride, right? Like really bumpy, lots of fluctuations, energy popping in and out everywhere, right? Like the one moment I'll be here, one moment I'll be like exploding in, gamma rays or whatever, right? But that doesn't happen, right? There is a consistent macroscopic world, and I guess going back to Mikey, um, so so our experience, yeah, is no more kind of intelligent than just gases, right? But this is what keeps me up at night. It is kind of crazy that a macroscopic world does exist. It is kind of crazy, right? Like, because when you understand the microscopic bits, it's insane that a microscopic world like this, like a sensible microscopic world exists. So this is what keeps me up at night. Like it's insane. Like reality is stranger than fiction. Like you can't dream this thing up, even if you try.
Fair, fair, fair. Yeah. So I guess we're definitely at time. I wanted to do a lightning quick round because there's one more audience question. So I'm gonna just go for it, and then we can call it a day. Do you think it's possible to ride a gravitational wave with a hypothetical ship that could potentially ride the wave as if it were outside of gravity and space and time?
I would. That's an interesting thought. I would say we are riding gravitational waves already, and as a matter of fact, you can't help it, right? And while I know we keep saying space time doesn't exist, but of course there's an emergent concept of space time that exists, and then there's an emergent concept of this space time web that is waving around, right? And if a gravitational wave is coming, to some extent we feel it, right? It's pulsating, although the amplitude is super tiny that you're not gonna feel it. You're not gonna feel anything. So you're not gonna escape gravity and space time. Let me just put it that, because we're part of it. Like you can't. Even if it breaks down, we will be part of that breaking down. So you can't really go outside of it. We're stuck with it. But riding it, yeah, we are already riding it. It's just that you will hardly feel anything. So.
Just to take that question to a microscopic level, so I don't know exactly what happened if you would ride a gravitational wave, but if you could actually make yourself so small and so delicate that you could ride on the back of a single graviton, you would see all the secrets. All the stuff we're talking about that we don't know about would be obvious to you if you could do that. Because if you can just make yourself so small and so insignificant that you can ride in a graviton, you would have access to. I mean, we know that certain types of particles are restricted from certain types of interactions, but for the graviton, there's no restrictions. That literally is fundamentally connected to the fabric of space-time itself, and so if you could actually, yeah, it would require you to make yourself very tiny and very light. I mean, massless to be exact. But if you could ride on a light wave, you would see all the secrets that were not obvious that Einstein elucidated. If you could ride on a graviton, all the mysteries we're talking about right now would become immediately obvious.
So how do we do that, Mikey?
This should be an episode of the Magic Yellow Bus, right? But
yeah,
we can't really do that. Sorry, we can do it in our head as theoretical
that
physicists.
Is like literally the final frontier.
All right. Any concluding thoughts before we head out?
Yeah. Well, I think I've said what I wanted to say. Reality is stranger than fiction. That's something I always like to think about.
Yeah.
I think my only concluding thought would be that, like, I'm happy that this idea of smooth space-time breaks down, because it means that there's like a way, like a piece of the puzzle that is just way deeper than we thought, and people are, like the the state of the art people working on these theories right now, they're really starting to get answers for what replaces space and time. Now that we know that it's doomed, and I think that's the most exciting frontier of research right now.
Very cool. Very cool. All right, then. On that note, I want to thank everybody for joining us, and we'll see you all next week, Tuesday at 5 p.m.
See you all next week. Bye
See ya.
bye.
Bye bye.
Bye.